Oh, okay. Uh, those of you online, can you confirm if you can hear me? Are you hearing me? Those of you online? Okay, thank you. Thanks for confirming that. Okay, I want to welcome you to another exciting statistical topic. Like I said, I need every one of you to be focused for, now, you know, the booklet, you can put that aside. I released this exam result on time so that you're going to have enough room to prepare for the final. Okay? So please, I want us to be focused on what we want to do, because what we want to do today is very, very crucial. And you need to be here physically and mentally for us to be able to grab. Okay, so we're still on repeated measure ANOVA. Okay, but except that today we're going to be comparing models. Okay, we could have different candidate models. Okay, and how do we compare them in a repeated measure ANOVA? I first want to appreciate those who actually provided feedback. Your feedback actually help a lot. Somebody asked me a question on what is the difference between a crossover design and a repeated measure ANOVA. Okay, somebody has this question. I know you have heard about crossover design before. Crossover design. Okay, and what is the difference between this and a repeated ANOVA measure? The crossover design is it's a generalization of a repeated measure. I'm going to tell you the difference now. When I'm talking about repeated ANOVA measure, okay, the participants were actually tested on a single treatment, except that they were observed at multiple times. I'm going to say that again. For repeated ANOVA measure, okay, the subject were actually tested on one single treatment, one single treatment. They were tested on one single treatment, except that they were observed at different times. That is what we call a repeated ANOVA measure. But if you want to talk about a crossover design, the crossover design means the participant will be tested on more than one treatment, on so different kinds of experimental conditions, and they're also going to be observed at multiple times. You can see the difference between the two. Okay, here it's just like they place me on a drug A here, and after I'm also going to go for drug B, the same person. That's a crossover, and they're going to observe that person at the except here there's something that we call washout. We have a washout period, and they consider what we call carrying over effect. Carrying over effect, because so that is that is the difference between the two. Okay, I'm going to say that again. The repeated ANOVA measure, okay, this participant, okay, the subject were actually tested on one single treatment, okay, and they were observed at different time. Okay, but for crossover design, the subject were tested not only on one single treatment, but on several experimental conditions, and they were also observed multiple times. Does that make sense to you now? Do you see the difference between the two? But we are focusing on a repeated measure ANOVA. Okay, now, like I said today, we actually want to compare models, okay, within what we're doing. Now, in the outline, I'm actually going to walk you through the nested ANOVA with a likelihood ratio test. The nested ANOVA is what we use, when we want to compare models. The nested ANOVA use, requires that you do your estimate with the method of the maximum likelihood. Then what are the models we're comparing? What are the models that we want to compare? Oh my God. When you take a look at model, we got some model that have main effects. Main effects. We have some models that have main effects. Okay. So we got some model that have main effects, and we got some model with the interaction effects. Okay, maybe here I'm talking about factor A, factor B, but here maybe I'm talking about factor A, factor B, and the interaction. Okay, so at times, how do we actually know whether we should go for model, okay, without interaction, and the model with interaction? Okay, of course, we're actually going to learn on how to compare models. And because of the fact that we actually are using the idea of a random effect, okay, the idea of a random effect is being used because of the fact that there's a correlation, okay, within subjects. You know, we may want to decide, should we use a model that have a random intercept with a constant slope, or should we use a model that have a random intercept and a random slope? How do we decide on a model that we're actually going to choose? I'm going to say that again. Should we choose a model, okay, with a random intercept, but the same slope? Or should we go for model with a random intercept and a random slope? Okay, and that is why today focus is basically going to be on comparing models. We want to compare models. Now, you know what I want to do? I want us to focus on the example that I used in this class the other time. That example has highly significant biological stuff. Take a look at this. We're talking about data where we're looking at the distance. We notice the changes in the distance from the center of the pituitary gland, okay, to the pterygomaxillary tissue, okay, which are very, very important in orthodontic therapy. We basically want to see, we notice that there's a change in that distance, and as a child is growing up, okay. And what is the significance of that pituitary gland? Why do you think they are interested in that? They're interested in that because that secretes hormones that are essential to growth and reproduction. That is why that very distance is of high significance to researcher. Okay, now we've been using this data where we got 27 children, okay, consisting of 16 males and 11 females. And of course, they were observed that distance. We actually observed that at the age of 8, when they were 8, at the age of 10, at the age of 12, and at the age of 14. Of course, that actually make the situation to be a repeated measure, because the children here, the 27 children here, they were actually observed, at 4 different times at different ages. Just basically want to see, is there going to be a change over time? Okay, so of course, the response variable that we're focusing on is the distance, right? And that's to be quantitative, that's to be continuous, right? Now, we now have some research questions in mind. Whenever we are conducting research, of course, we basically want to provide a practical answers to practical problems. And what are the questions we have identified? Question number 1, does the distance change over time? Over time means as a child is growing up, okay, do we notice, is there a significant change in the distance that we're talking about? Then another question is going to be, what is the pattern of the change when you look at the pattern of the change, is there an appreciable upward movement or downward movement, or it doesn't really change at all? We actually want to know that. Then the last one is that, is the pattern different for male and female? Don't forget, the 27 children we're using, we got 16 males and 11 females. And we basically want to see whether the pattern, the pattern of changes that we're talking about, is it going to be the same? Okay, we want to see whether male and female, they're going to have a similar experience. Does that make sense? Okay, now this is the data frame. Okay, the data frame, we of course, we're going to be 1 to 27, don't forget. Or we got 27 children, right? And in these 27 children, we have male and female, right? And that was why you can see, and they were actually observed, at 4 different times, at the age of 8, at the age of 10, at the age of 12, at the age of 14. Okay, the values that you are seeing, 21.0, 20.0, they are the continuous random variable that we actually call the distance that we're talking about. Okay, does that make sense, right? Okay, now take a look. If you take a look at this now, this is our data. Now, the last time we met, I only focus on female, and I'm bringing that back. We may want to focus on a particular gender where the interest is on, okay, let's look at what happened for female, or we want to look at male. Okay, now when you take a look at the data you're seeing now, we're actually focusing on female, and that was why you see gender equal to F. Okay, focusing on female, okay, we actually run a regression. Okay, where the age is basically going to be an explanatory variable, and the distance, take a look at that. We're using the female data. We actually want to investigate relationship between distance that we talk about and age, and we're only focusing on female. Okay, now focusing on female, we are actually treating age here as continuous. I want you to take a look at the output now. We actually treat, even though we actually collected the data from female on 4 different occasions, okay, we're not interested in the categorical level of age. We're treating age as continuous. And if you take a look at this result, we are assuming independence. I wish I know, because we observed this female, we visited them at the age of 8, 10, 12, 14, then it means they are not likely going to be independent. So which means the output that you see, okay, okay, is going to be misleading. Because one of the assumptions of linear regression is that there should be independence. If I can remind you of assumptions of linear regression, we have linearity, we have normality, we have a constant variance, okay? And we have the absence of outlier and so on like that. But if you notice, if you take a look at the female data we use, okay, before you can use a linear regression of this form, you are assuming independence. We should know they are not independent. So which means this cannot be trusted, okay? This cannot be trusted in the sense that, okay, we are assuming no correlation. And I show you theoretically, right? The other time when there's a correlation and you are assuming no correlation, that will tell on your error. Okay? When you make a mistake in statistical analysis, or maybe fitting an inappropriate model, okay? What will be the consequence of that? The consequence of that is basically going to tell on the residual. So therefore, you can't trust this. And what do I need to do? If I basically, if I don't want to mislead, what I'm going to do is to incorporate a statistical approach that we consider correlation. And the only way I can do that is to introduce a random effect, which is what I want to do now. Oh my God, take a look at what I'm doing now. I'm introducing random effect for female. Don't forget, I'm focusing on female. Why do I introduce a random effect for them? I'm introducing a random effect because introducing a random effect has incorporated the fact that correlation exists. But if you take a look at the other one, this very one, okay, it's assuming independence, but which we know there's nothing like independence here, because the participant were visited in more than one occasion. And that was why we are now assuming a random intercept. We're assuming a random effect for female now, for the subject. Right here, the random effect is for the intercept. We're assuming that, okay, you know what? The subject, they're going to have different intercepts, but they're basically going to have the same slope. I'm going to say that again. The subjects, they're going to have the same different intercepts, but they will have the same slope. Now, if you take a look at the code, module _1, okay, distance is the response, right? Then I bring in age plus 1, okay, you're going to see a vertical bar subject. Now, the vertical bar subject is trying to tell you we're making subject to have to be a random effect, okay? And that one means we're assuming intercept, like we're assuming a random effect for the intercept. That is why the subject is nested in one. One indicates intercept. You can see that there's another explanatory variable out, which is age. It's missing that module. I'm only looking at the fixed effect of age and the random effect of subjects. I'm going to say that again. Let me tell you this. I understand my statistics. I understand my mathematics because I relate to real life. I want to see what I'm teaching. If you're teaching me something, if I'm not seeing it, how am I going to see what you're teaching me? I need to relate to real life. Because if I don't relate that to real life, it doesn't make sense to me. It's basically going to look like an abstract to me. And that is the reason, my experience teaching in Africa, Europe, and this part of the world, I realized that students that struggle with mathematical concepts, they don't normally relate whatever they learn to real life. I'm going to talk about that module again, module _1. The module _1, I'm actually looking at a fixed effect of age and a random effect of subject. And what I'm choosing to be random there is intercept, and that is why I'm actually nesting subject in one. Any question on that one? Therefore, this is a mixed effect model. Why is it a mixed effect model? Because we got a combination of a fixed effect. Fixed effect in this case is age, and the random effect in this case is subject. Then what am I expecting? I'm actually expecting two different results. I'm expecting a result that has to do with variances. I'm expecting a result that has to do with effects, and that is what you've seen on the board. Now, let's take a look at the one for the random effect. You're basically going to see variances. Now, let me tell you the mistake some people made in the exam, midterm 2. When I asked some people to calculate ICC, inter-class correlation, they were using standard deviation. You are not supposed to use a standard deviation. You are supposed to use a variance. If you take a look at the output here, you can see variances, right? You can see standard deviation, right? And if you look at the random effect, okay, we normally talk about variance. Does that make sense? So please watch out. Now, as you can see, there are two different forms of variances. Variance of the subject and the variance of the residual. If you want to talk about the variability in the system now, you're actually going to talk about the variance of the subject plus the variance of the residual. That is the total variability. Of course, the age, being a fixed effect, doesn't have a variance. Of what is the variance of a fixed effect? If I have 5, what is the variance of 5? It's 0. Because 5 is a constant, it doesn't change. Okay? Now, if I want to take a decision now, if I want to take a decision on age, because age is a fixed effect, I can use the p-value here associated with the age. Okay? But if I want to take a decision with the subject, because it's a random effect, there's something need to be done. Because what I only have on the board, I only have the estimation for the variance. You know what we normally do, right? If I want to test the significance of that, maybe I'm actually going to use the method of the restricted maximum likelihood, where I'm going to load a package, and the package will come with the p-value. Okay, now we're going to have a random effects for subject. Okay, all the subject. Then if you take a look at the other side, you're going to see for age, the slope remain constant, but the intercept varies. Why do we have that? Of course, we have this because we're assuming a random effect for the intercept. We're using random effect intercept for the subject. And that was the reason. Now, what is new? I'm going to show you what is new now. I want you to take a look at what I'm showing you now. Please, I need you to pay attention. Up to this moment, I was focusing on female. I wanted to focus on the board. Up to this moment, I was only focusing on female. But right now, on slide 14, or on slide 14, I want to focus on both male and female. I'm going to say that again. I want to focus on both male and female. If you take a look at, why do I have 11? Why do I have 11 subjects here? Because I was only focusing on female. If you take a look, how many female do we have in this study? How many female? We got 11 females. Okay? What we've been doing before now, we didn't focus on male. Now, right now, we now want to focus on 2 of them up together. Okay, starting from here. And if I want to focus on 2 of them together, I'm actually going to assume a random effect. Now, the random effect that I'm assuming now is for the subject, and that very subject is not going to be 11 anymore, but it's going to be 27. It's going to be all of them. Does that make sense? Now, if you take a look at what is the difference between this model and the last model we fitted. In the last model, we only focus on female, but right now we're focusing on everybody. And that was why, because we're focusing on everybody, then we need to introduce another explanatory variable that we call gender. Can you see that gender now, right? Gender, which is categorical, which is telling you, okay, we're going to be focusing on both male and female. Now, I wanted to take a look at what I have now. We have age. In that model, we have age. We have gender. Age is fixed. Gender is also, of course, we got 2 levels, fixed. But the subject is random. Take a look at that now. This is an extended model. Now, by the time we run that, okay, so what do we have? This is going to be the result. Okay, we're getting the random component. Okay, but in the fixed effect side, don't forget, there are 2 explanatory variables that are fixed, right? Age and gender. Now, why is the R reporting gender M? Because R has automatically coded male as 1 and coded female as 0. But let me tell you this. You know, when you have a categorical variable and maybe there are 2 levels, if I code male 1 and I code female 0, that doesn't mean male has a numerical advantage over female. That's not what we mean. It's just a labeling. Does that make sense? No any numerical advantage. Okay, now because I'm seeing a gender M appearing in my arrow output, what is telling me is that R, okay, has automatically coded male as 1 and coded female as 0. Now, if I want to look at the effect of age now, I'm just going to look at the p-value associated with age. If I want to look at the effect of gender, I'm actually going to look at the p-value associated with that. Now, when you take a look at the age is significant. The age that is significant is just trying to tell you the distance at different time, they are not the same. Gender being significant means the experience is different between male and female. Does that make sense, right? That is the story. That's what the story is about. Okay. Now, if you now take a, if you take a look at what we've done in module 0, look at that module 0. We have 2 factors that are fixed. We did not consider interaction. Okay. But do you know there is possibility that they could interact? And that's what I want to consider in module 1. Take a look at this module now. Module 1. What have I done? In module 1, I'm now putting into consideration the interaction between age and gender. Why do you think I'm doing that? Maybe age as a factor is not consistent in terms of behavior. I'm going to say that again. Maybe age as a factor is not consistent. Okay. Maybe the behavior of age, okay, is different at different levels of gender. And that's why we need to test for interaction. If the interaction is significant, you know what that means? Then it means factor age, okay, does not have a consistent behavior. But when the interaction is not significant, then we're going to say it has a consistent behavior. That's exactly what we mean. Okay, now we fitted, we're still using random intercept, okay, and we fitted this. Now we have results. Now let's look at the fixed effects side. In the fit effect side, oh my God, take a look at the interaction in the fixed effect. It is significant. That significance is telling us a new story. The story, which means age, okay, even though the distance we're talking about changes over time, okay, but that very time, that age now, okay, depends on whether you are female or male. Because of the fact, look at the interaction, it's significant. Okay, now we got 2 different modules. Module 1 with interaction, module 0 without interaction. Okay, we got 2 different modules, one with interaction, the other one without interaction. Now these 2 modules are before us. Now the question now is, do we have a criteria in statistics to be able to choose which of the 2 modules is the best? I'm going to say that again. We got 2 competing modules now, one with the interaction and one without interaction. Now, and that is the reason why we now want to, like, okay, can we have a way to compare them? We want to take a decision. Should we go with the one without interaction, or we should go with the one with the interaction? And that is what we want to do now. Now, the method that we use in statistics to do that is what we call the likelihood ratio test. We're going to get a likelihood of the first module and the likelihood of the second module, but there's a condition. There is a condition. The 2 modules have to be nested. What do I mean by nested mode? I'm actually going to write something now. Okay, what do I mean by nested model? You know, the simpler model will be under the HO. Okay, the simple model will be under the HO. Maybe this one is the one I saw, regressing this with this. Don't forget, you have X3 that is actually random effects. Okay, and HA Y on X1 plus X2 plus X1, X2, okay, plus that, okay, this is the interaction, right? Now, when you take a look at these two model, the first model is inside the second model. That's what we call nested. Because the only difference between these two models is just interaction. So if I want to test now, which of the model am I going to choose? Okay, I'm actually, before I can use the likelihood ratio test, okay, then I have to make sure I'm actually working with a nested models, where the simple model is actually contained in a complicated model. And let me tell you this, the null hypothesis HO, we always have the simple model. The alternative, we have the complicated model. Okay, in statistical analysis, we don't choose a model because of simplicity. We don't choose a model because of complexity. We actually have a model selection criteria that we actually choose between them, which we call the method of likelihood ratio test. But the method of likelihood ratio test, we actually assume that, okay, you've used the method of maximum likelihood to estimate parameter in both models. Of course, I think I walked you through the method of maximum likelihood the other time. Okay, which is so in the end, we're just going to find the difference between the likelihood of the HO, the likelihood of the alternative, then we're going to multiply by 2. Okay, and that is expected to approximately follow chi-square distribution. Okay, so, and that was exactly what I'm trying to, and we have other selection criteria we can use to select competing models in statistical analysis. I can talk about the AIC. Maybe I get the AIC for the first one, get the AIC for the second one. The one with the minimal AIC is a better model, or the one with the minimal BIC is a better model. Okay, so, but now take a look at it. We're using likelihood ratio test. Now, there's something I want to pay attention to. I said the likelihood ratio test, LRT, is twice the difference between the log likelihood at the MLE minus the log likelihood under the null hypothesis. So which means I will need to get the likelihood function for the simple model, the likelihood function for the the complicated model. But we know, in order to make things easy, we can take the log of the likelihood. Okay, we take the log of the that's why we normally use log likelihood, log of the likelihood. Then at the end of the day, we're going to subtract them and we multiply by 2. But let me tell you this. Unfortunately, we say that when we have two different models, simple model, complicated model, and they all have fixed effects. Okay, they all have fixed effect. Okay, the distribution of the likelihood will follow chi-square, but the one we're considering as a random effect. And that was why we say, unfortunately, the chi-square approximation in step 3 is not a good, it's not good for testing random effect. If you go to step 3 now, look at the step 3 here. Set the chi-square degree of freedom to the different, because if I want to figure out the p-value of the test, I need a distribution. Okay, and we've been using chi-square distribution for fixed effects, but right now got a random effect in our model. So what's going to be the way out? The way out is going to be through simulation, and that was why I said to get beta p-values, we can simulate the distribution of the chi-square test using a function in R. Of course, my TA is going to walk you through that. But let's take a look at this. If we want to compare two models that are nested, using the likelihood ratio test, we're going to use ANOVA function. We're going to write ANOVA in parentheses. The first module that I'm actually going to write will be the simpler one, followed by the complicated one. Can you see what I have? ANOVA into module 0. Module 0 is a module without interaction, and module 1 is the one with interaction. Now, this is what you're going to see, this result. What are you going to pay your attention? And in the output is going to tell you what you're doing. Okay, look at the object. The first one, you only see age plus gender, right? The first one is only talking about the main effect of age, the main effect of gender. Don't forget, the main effect of age, the main effect of gender, they are both fixed, right? And with the subjects are random. But when you take a look at the second one, you have the interaction. Now I need you to focus on the p-value. Oh my God, you need to focus on the p-value. But before you go to the p-value, you need to first write your HO and HA. Okay, you know what HO means? The simpler module is appropriate. You know what HA means? The complicated module is appropriate. What is my simpler module? Module without interaction is fantastic. What is my alternative? Module with interaction is fantastic. Now, look at the p-value now. The p-value that we got is 0.01265 is less than 0.05 standard level of significance. What are we going to do? In statistical analysis, when p-value is less than a given level of significance, you're basically going to reject the non-hypothesis. What are we rejecting now? We are rejecting simple model, a model without interaction. So which means our conclusion will be on what? We're going to conclude on the model with interaction. But do you know, I knew this from day one. You know why I know that? I know that, right? I'm gonna show you something now. Why I know what the decision is basically going to be. I'm going to show you now. Oh my God, I know from here, look at the age, look at the interaction, turn out to be significant here. But in order to have more convincing part, we can actually go for the likelihood ratio test. Now, that is a likelihood ratio test. Any question? And do you know if you want to use the AIC, take a look at the AIC. Which module has the lowest AIC is the second module. Look at 444 and 440. If you look at the AIC, if you look at the BIC, you're basically going to say, is it going to favor the complicated module? Okay, does that make sense, right? That is it. Stat is easy. Statistics is easy. You know, the only thing you just need to look out for is just like, okay, how does this technique work? Why do we do this? Why do we do that? Any question? Okay, now the model we have fitted so far is this model. We have X, age, gender, and the interaction. And of course, we have, this is specification where, of course, don't forget we're using the random intercept. This is the graph. Okay, this is the one with age, gender, and age. This is the one with interaction. They are not the same. Look at that. This is the one with main effect, the simpler model. This is the complicated model. Okay, I want to take a look at that. Now, what does this model mean? The result that we got now, what does it mean? Okay, and I said, are the mean response profiles similar over time? We want to look at the effect of age for the two genders. Are the plot parallel for two genders? This is addressed graphically by assessing the time gender interaction. Of course, if you want to test for parallelism, you test for the interaction. When interaction is not significant, that's a parallel. When it is significant, that is not parallel. Okay? Do the mean response change over time? Is the mean response for the time flat or not? And that addresses the time effect. Is there a difference between two genders? If I want to know whether a difference is between two genders, we'll look at the p-value associated with gender. Okay. Now, and don't forget, the random effect are the subject specific. Okay, that I plotted here. I quickly want to move. I'm not going to start here today. You know what we're going to start next time? We're still going to use this material next time. I see you have like 10. Can somebody, I want to award an extra credit now. Okay, I remember this. You've seen your grade for midterm too. For those of you